I'm Gerald Pollack, professor at the University of Washington in Seattle, and author of the fourth phase of water. My latest book, which is why I'm presenting to you, is called Charged: The Unexpected Role of Electricity in the Workings of Nature. Why electrical charges in nature? Well, as an undergraduate, I studied electrical engineering, so I did get some grounding in the principles of electricity. And early in my career, I was exposed to something that I didn't understand, and finally, I could understand that electrical charge had something profound to deal with that, and also other phenomena that are sort of loosely related to that, and it had to do with sailing. So I moved from the East Coast to Seattle at the University of Washington, and I think perhaps as a lure to make new faculty members welcome, they offered sailing lessons. You know, in the Northwest, full of winds and full of water, sailing is very popular. So I signed up for the sailing course, and they offered a book, and I purchased the book and started reading the book, and I could quickly understand how you could go downwind when sailing. You know, the wind, the sail catches the wind, and the wind pushes the boat, and the boat goes downwind. But I found out that sailboats also go upwind. Well, not exactly upwind, but typically they, like the kinds of boats on which we were learning to sail, they would go perhaps 45 degrees off the apparent wind. So there's a component of force that goes into the wind. And I really couldn't put my head around that, going into the wind. The book described it, spent a few chapters, and I figured that, you know, the boat could do it, and the book described it, and therefore um, the principles must be well understood as described in the book. But it still didn't make sense to me, and I figured it must be a deficiency on my part that, you know, I thought I could understand things pretty well, but apparently I couldn't understand this. Well, then I found out later that there are boats that go not 45 degrees off the wind, but the boats that participate in races, racing boats, they can do something like 30 degrees off the wind. And then, to my astonishment, much later, I found out that there are boats that go only 5 or 6 degrees off the apparent wind. Uh, that's almost directly into the wind. Now, does that make sense? I learned quite a bit about forces and the role of forces in nature and in engineering, and it just made no sense. It's like I'm blowing a fan on you, and you'd expect that you'd go backwards, but in fact, you're coming toward the fan. Uh, Completely opposite to what you would expect, and I simply couldn't understand that. And finally, I came to the conclusion that, well, you know, maybe everything that you read in the textbook is not necessarily correct. Uh, that was and Eventually I recognized that what played a central role was the force of electrical charges repelling or attracting one another, and not only in sailing, but in also in other phenomena in nature, many other phenomena. And we think we think that charge forces, you know, are trivial. I think most people think so, but it's not the case. In fact, it's not the case at all. And I would like to share with you something that comes from, not from me, but Richard Feynman. And Feynman was a Nobel winning physicist, and he was considered by many people to be the Einstein of the second half of the 20th century. And in his book of lectures, he discusses what happens, or how large the forces of charges can be. And he illustrates with an interesting example. So, and I'm revising only slightly. So let's say you and your partner, you lie down on the ground, and your partner is suspended above you, 1 meter, 3 feet above you. And the manner of suspension is not too important. It could be like a hammock or something. Your partner is resting on the hammock. And then suppose you can remove 1% of all your positive charges in your body, 1%, and 1% of all the positive charges in the body of your partner. So the two of you are, each one of you is negatively charged. Now, if you're negatively charged and your partner is negatively charged, you repel one another. Well, you can't move down because you're lying on the ground and the ground is solid. But your partner could actually move up. And the question is, how strong is this force? Or put a different way, how much weight would you need to put on the back of your partner so as to prevent him or her from rising upward? I've asked this question many times to many people because it's a kind of fun issue, and I got responses something like, oh, well, maybe 50 pounds or 100 pounds, or maybe the weight of the person. And the real answer, as computed by Feynman, who is considered like, well, one of the top mathematicians in the world, he calculates that the weight that you'd have to put on the back of your partner to prevent an upward rise is equal to the weight of the Earth. Phenomenal. Now, if that doesn't prove that charge forces are immense, I'm not sure what will prove it. And the book's subject matter deals with everyday phenomena that you see all the time. You think you understand them, but the book demonstrates that there's enough disagreement with facts that you really don't understand them. And charges turn out to be extremely important. So the book subject matter is, as I said, is everyday phenomena. And besides sailboats, I deal with a bunch of questions. And for example, what turns the Earth every 24 hours? It does turn. You need a force to turn it. Where's the force? How does it arise? What makes the wind blow? You're sitting in a rowboat in the middle of a lake, and suddenly the wind blows, a gust of wind. How does this happen? What causes it? And then there's weather, which obviously we're exposed to all the time, and simple questions that you see but you don't really think about. How does a cloud form? A cloud seems awfully mysterious, and what suspends the cloud in the sky? You know, if you take some droplet of water, the cloud is filled with droplets. If you take a droplet of water and you let it go, it goes down, but the cloud stays up. Mostly it stays up. Why does it stay up? What force is involved in that? And sometimes it rains. A cloud unleashes its water, but not always. So what turns on the switch? How does the cloud decide, or what decides whether it rains or it doesn't rain? And what creates a tornado that can lift a school bus? How does that work? You know, these things occur. We hear about them on a regular basis, but we don't understand any of them. And then there's another issue. Then is the force of gravitation. You know, your rear end presses firmly on the toilet seat, and it's because masses attract. Your mass attracts the mass of the Earth. But how does that explain a published finding from an Italian group continuously measuring the gravitational force? They find that in summer, the gravitational force is higher than in winter. Weird. How does that? And another group, in fact, a group from MIT, finds that the gravitational force undergoes a periodicity. It's 24-hour periodicity, stronger in during 12 hours and in the subsequent 12 hours, and repeating that. How does that happen? How can that be if the force is simply one mass attracting another mass? And then finally, flight. We all think we understand flight, right? We fly in a Boeing 737 or whatever plane we wish, maybe a 747, and I guess is where we want to go. And the theory that's been around for a while is that the plane achieves lift. It achieves lift by virtue of the curvature of the wing. The top of the wing is curved in an airfoil shape, and the bottom is flat. And because of that, according to Bernoulli's principle, because the pathway of a molecule of air, the pathway is longer on top than it is on bottom. The pressure on top is lower than on bottom, and the plane achieves loft that way. And that principle is observed not only in planes, but also to some extent in birds, which also fly, some of them without flapping their wings. So if that's true, then how do we explain why you can buy a hobby plane with I've done it, with wings that are flat on top, absolutely flat, and flat on bottom, and they fly perfectly well. And you can fly them either as they are, as they come, or you can attach a motor to them and they fly also, but no curvature on top. How does that work? And what about paper planes? There's no curvature there. And paper planes, maybe your paper planes can go only 10 feet or so, but the record is, if I recall, somewhere around 200 feet, almost the size of a baseball stadium. No curvature, but they fly perfectly well. And then there are planes that fly upside down. And even a report some years ago, sighting of birds that fly upside down. Now, if it's the top of the wing's curvature that keeps them aloft, then you'd expect that if they fly upside down, they would plummet. But obviously, they don't plummet. And then another example is insects. Some insects can fly straight up. How do they do that? And also flat wings. How do they fly straight up? No curvature. So those are all some, you might say, acrobatic feats, but we see them all the time, but we never think that there's some violation of the Bernoulli principle. How do these things work? And is it possible that somehow charges are involved? And of course, what I will demonstrate is that they're centrally involved in flight, both in keeping the plane or bird up and also pushing it forward. So the book addresses all of those phenomena, plus other phenomena that I'll skip here. And it offers a straightforward understanding based on the force of electrical charges. Electrical charge is absolutely central for all of nature. And I attempt to explain how they work in terms simple to understand. And they're made simpler by the beautiful diagrams of my son, Ethan, who's a gifted artist, whose art is simply beautiful, and color illustrations that even have a tinge of humor to them. I attempt to explain with verbiage that I attempt to make really simple, straightforward, so that you don't need a PhD in physics to understand what I'm presenting. It's fairly straightforward, and I hope you will enjoy reading it as much as I enjoyed writing it. Thank you.